Right. I'm pretty sure now you notice that riders won't go anywhere until you master them, isn't it? So please master them already so they can go away from us. Now, what is it that I want us to do? Firstly, let's prove that this thing is a cyclic quad as we have been told. There are things that we can see already, such as TD is a tangent on this diagram. Can you see where TD is? This line right here, it's only touching the circle, just touching. So it means we have an angle between a tangent and a chord right there, which is D3. Are we happy with it? D3, even D2 and 3 can be seen as the angle between a tangent and a chord. Okay, then we also have some parallel lines. Very clear to us that these lines here are parallel to each other. No stress. Then let's quickly figure out some more given information. I believe this is going to come in handy. You know, the fact that S4 is equal to S2. Let's just keep that in mind. For us to really get there, I'm going to highlight the cyclic quad that we have. So we have SW. This is the shape that we want. So this is the shape. I think we can see the shape. This is the shape that must be the cyclic quad. SWTD. SWT. Okay, I believe this must be the shape. So for this one, I can see we could have used also exterior angles, but the main thing that's standing out right now is that there is a bow tie inside. Can you see that? So since there is a bow tie we can see inside this shape, we must actually try to focus on getting the converse of angles in same segment. Do you see this bow tie that's inside right here? So we can easily prove anyone, let's say for example, if we manage by any chance to prove that D2 is equal to T2, we will be done proving that this thing is a cyclic quad. But I always say, if the angle, do you see where T2 is? We may not be able to find any angle equal to it because it is outside the circle. Very difficult if it is out there. The same applies to maybe if you choose to use W2, can you see you have to prove that it is equal to all of this? Again, W2 is far out of this circle. It will be difficult to get it as well. So whenever you have something like this, I always say, try to pick the ones that are next to the circle if possible. So if I see this bow tie in a different angle, like for example, look at this S4. If I prove that it is equal to D3 one way or the other, do you see that I'll be done with this bow tie? Can you see that? Okay, so what we are going to do is to prove that S2, if you look at this, I'm sure you are looking at the bow tie which we are using at this point, we'll be saying then if these two angles are equal, then it must mean that that thing is a cyclic quad. So let's go and try to prove. We have targeted two angles. We targeted S4 and D3 here. If we can prove that these two are equal, then we know that our lives will be right in order. So let me remove everything that we don't need so we can start seeing a few things. It doesn't matter what you start with. Maybe you start by finding angles that are equal to D3, or you find angles that are equal to S4. I believe the easiest is to start with the information that was given. Do you see that S4, if I start there, S4 is equal to S2, it was actually given to us? Can you see that? So at this point, that's a good thing, because I was going to struggle with S4 because S4 is also kind of outside the circle. The only thing I could have done there was to say S4 is equal to S6. Can you see that? And that was going to be vertically opposite angles, and maybe then from there I was going to find a way out. So for now, I just went for the given information. Now, S2 is at a place which is very, very interesting. Can you see where S2 is? Now, S2, we can easily equate it to what? To D3. Okay, I was looking actually at D1 at this point because I was busy using alternating angles. But if I use D1, then I won't come back, because at this point, S4, well, maybe we'll eventually get to D1, but I believe the fastest way, yeah, you can still do it, I saw. The fastest way will be to say the S2 that we have here is actually equal to, did you say D3, right? Yes. Because it's the angle between, this angle between a tangent and a chord, it will be equal to the angle subtended by that same chord. So at this point, I can really say D3 itself, because that's the one we want. But we know that D3 itself is actually equal to S2. And the reason is Tan-Court theorem. We are using the theorems that we know. Now, after making these two statements, how many of us can see that we can conclude that since these two angles are equal to S2, both of them, we can conclude that therefore S4 must be equal to D3. Now, the moment you prove that those two are equal to each other, then you can say as a result of all of this, it means that SWTD must be a cyclic quad. And why are we so sure? What short reason did we say we use if we use kind of these angles in same segment, if we use the bow tie? So this time is the converse. We noticed that angles subtended by the same chord are actually equal. So it's converse angles in same segment. It's a skill, this one. So once you get used to it, then you can do it. I just want to do it in a different way, but still targeting the same one. So let's just do it because we can. I mean, I just want to accommodate those other ones that used a different one. So let me say or here. We are still targeting the same thing, that S4 is equal to D3. I'm not going to change that because I am seeing that that will be the fastest way of doing things. Let's do it in a different way so you can see that it's possible. Now I'm going to erase all of this. So firstly, I am going to go for what I said was easy to see, but I don't know if we will be able to come back with D3 now. Which angles are equal to D3? It is S2. Let me come from D3. Let's see. If I go and say D3 is equal to S2, I believe this one, we can't avoid it. That's Tan-Court theorem. I'm trying to go via that other one. Let me see. I'm going to miss one step and see if you are going to come back. So I'm saying this angle here is equal to this angle, but S2 itself happens to be equal to D1. I want to go via this person who will see the alternating. Do you see the alternating angles? So let's see if this person will be found. So this is true because they are alternating angles, but the parallel lines are DR parallel to what? PS. I see. Okay, so for now, let me just make a conclusion right now. Can I because you don't want to keep on going. If you keep on going, you'll forget what you're doing. By doing this, I have proved that D3 is equal to D1. Is that fine with you? Okay. Now, remember what we want to prove. We want to prove that S4 is equal to D3. So can I make S4 equal to D1 right now? I believe I can. How am I going to do so? I'm going to first of all mention that S4 is equal to S6, isn't it? Now, I wanna avoid using the given information. Can you see this vertically? I'm just trying to do it a different way. Do you see these ones? They are vertically opposite each other, right? So I'm going to say S4 is equal to S6. These are vertically opposite angles. But was this given to be a tangent? Please say yes.
No.
This is not a tangent here. Really? Oh, I was of the idea that it was. Are you sure? Okay, well then we can't carry on with what we're doing because it was going to work if it was a tangent. So it means this was the way to do it, because then if it was a tangent, can you see I was going to say, but S6 is equal to D1. So at this point, then this method won't work, unfortunately, for whoever was going this way. Okay, so let's stick to that one method, because this one won't work because that is not a tangent. I was looking at it as one all along. All right, now we don't just say something is a tangent. I think you noticed it looks like a tangent, but we cannot conclude it is until we really prove that it's a tangent. So there are ways in which we prove that things are tangents. I'm going to show you the fastest way, but for this question, it's really not going to work that well. But let's see. I'm going to say, look at number 2. Let's find TK. TK is this line, isn't it? They said, prove that TK, this one, is a tangent to the circle at S. So if it is a tangent, you just have to prove that maybe, for example, this angle, if you can prove that S3, if this was a tangent, S3 was supposed to be equal to D2, isn't it? I can go and prove that. Or I can prove that S6 is equal to D1. Can I prove that? I think we can prove that one. So let's go and prove. If I prove that S6, so my mission is to prove that S6 is equal to D1, because I think that's the side that's a bit easier. S3 and D2, we don't have many. We never talked about S3, we never talked about D2. So but we talked a lot about D1 at one point. Now, can we mention that D1 is actually equal to S2? Okay, let me do that. D1 is equal to S2. What's our reason? Alternating angles. We did this before, and now it feels funny that we are repeating it. DR is parallel to PS. Perfect. I managed to prove that D1 is equal to S2. Now, the next thing I'm going to say is S4 is equal to? I think I need my S6 somewhere. Do you know that? I need S6. So can I say S6 is equal to S4? What's the reason? Vertically opposite angles. Now, but let's do this. But S2 is equal to S4. This one was given. What can we conclude about D1 and S6 then? Can you see the reasoning process? Can you see it? Yeah, we said D1 is equal to S2, and we agreed S6 is equal to S4, but these two angles are already equal to each other. So then what can we conclude about D1 and S6? Therefore, because of all this, D1 must be equal to S6. And the moment you prove this, then you are done proving that that line is a tangent. So we are going to say, therefore, what is the name of this tangent? TK is a tangent. Let me show you the short reason. Therefore, TK is a tangent to the circle. Okay, you can mention the circle, and the reason is you always put converse. You're not going to say tan chord theorem as if it was already you say converse tan chord theorem. Now, let me just tell you what they do normally with this converse stuff, the tangent, before we go. I think I say that in your first lesson. Did you watch that one already? Where I explained how to prove a tangent. Are you done with that one? Okay, so let me show you how it works. So what they do, if they give you a circle, well done. But most of the times they do not. They won't give you a circle. They will just say, prove that. Say, for example, let's just have some random line. Prove that PT is a tangent to a circle passing through point TBC, for example, like this. And you will go, let me repeat my question. The question will say, prove that PT is a tangent to the circle TBC. And then when you try to go to find that circle that they are talking about, what you will find is actually a triangle. Okay? Look at how TBC looks like. So how do you prove that that thing is a tangent? In other words, they are saying there will be a circle passing through those points. Forgive my circle. So if there was a circle passing through those points, this thing was going to be a tangent at this point, isn't it? So what you do is the first time the line touches the shape, this is what they are calling a tangent. It's touching this triangle of ours first at this point. So this is the angle that is going to be between a tangent and a chord, if it was a tangent. And it was then going to be equal to which angle, people? It was going to be equal to angle C. So what you will be expected to do is to prove, let me call it T1, T2, is to prove that T1 is equal to C. If you can prove that, you will be sorted. That's all you would do. It sounds very weird at first, but once you start doing it in real life, you will see how easy it can get. But before I show you one that looks like that, let's answer this C question here so we don't have to leave it behind. So let's answer the C question and then we can see what's happening. This topic has always been good at defeating you, isn't it? So let's quickly figure out, can I erase everything here? All right. Notice what we want to do. The parallel lines are equally as simple. I am going to prove that these ones are parallel with you just now. So look at this. It's just that this question has a lot going on, so we have to do everything it appears. Okay, here. They want us to prove that TW is parallel to PS. Let me go to the line. Let's highlight it. This here is TW. There we go. And then it is parallel to PS. Did you find PS? This one. If it is really true that these ones are parallel, just think about it. If they were parallel to each other for real, if we didn't have to prove it, there will be some corresponding angles and some alternating angles, isn't it? So, according to you, which angles will be alternating that you may want to mention? T2 and? P2 and W2. So you are saying these two angles must be they should be equal to each other. So here is what I'm saying. If you, by any chance, using any method whatsoever, prove that P2 is equal to W2, then you are done, proving that they are parallel. So why don't we use that method? Why don't we use the angles you chose on your own to prove this? Guys, do we have any angle that we know that is equal to P2 right now? I am seeing one and I'm hoping that you can see it too. It is? I think you chose the difficult one, but anyways, let's just see. Yes, dear? Of a cyclic quad, isn't it? So P2 is equal to R. Well, that is very good. P2 is equal to R, but we have to find angles that are equal to W2. But don't forget something, guys. Do you remember that we learned that there is another angle that is equal to P2 that I can't ignore? But anyways, before we do that, we proved that that thing was a cyclic quad a few minutes ago. Okay? 23. Okay? So, yeah. So what we are going to do is we prove that this thing is a cyclic quad at one point, this one. Now, once you prove that something is a cyclic quad, you are free to use angles. Now we have proved that there is a circle passing through those 4 points. So you can start seeing that circle, even if it's not there. So at this point, I can really say, I can go ahead and say D2 is equal to T2, and I'll say angles in same segment, as if there is a circle. Can you see what I'm saying? because we are done proving that there is a circle right round those 4 points. So what I am saying is, when you say W2, you said let's use W2. I can see W2 is equal to, can you see, to be equal to S3 and 4. So I want us to use it so you can be free to get to the answer. All right, here is what we are going to do. Let's do it slowly. Okay, first of all, let's write the fact that P2 is equal to, I'm going to say P2, I'm going to use the method you suggested. P2 is equal to R, and that is exterior angle of a cyclic quad. Are we fine? Okay, you saw that cyclic quad. Perfect. Now, the next thing I am going to say is that, what is this angle we talked about now? This one? You remember it? It's S2 and 3, isn't it? I'm going to use, we already proved it was a tangent, isn't it? Okay, perfect. So it means now this angle is between this tangent and this chord. You see that? So this angle as well is going to be equal to R. Can I do that? Okay, as long as you're seeing it. So S2 and 3 is going to be equal to angle R. And your reason now is tan chord theorem. I'm sure you are still seeing something. So what can we say about P2 and S2 and 3? They are equal to each other. Let's make that conclusion. Once you, I always say, make 2 steps and conclude, 2 steps and conclude. Otherwise you will, if you make 5 steps, you will lose yourself in that whole thing. Okay, so before we go anywhere, after making these 2 statements, we are free to say, therefore, P2 must be equal to S2 plus S3. This is a therefore thing. And wait for it. What did we say W2 was equal to? W2 is equal to S2 plus S3. Why am I so sure? Angles in same segment, like so. Okay? Are we together? Now, can you see which 2 angles are now equal to each other? What conclusion can I make from those 2 statements? P2 must be equal to? Remember, that was our target. We got there. So therefore, P2 is equal to W2. Now that I proved that angles that are supposed to be corresponding are actually equal to each other. So I am done showing that those 2 lines are parallel to each other. So I can go and conclude and say, therefore, as a result of all this, what were the 2 lines? PS and PT. TW. Now, you don't just say, therefore, PS is equal to TW and you go home. No. You have to give a reason. Why did you say that? Because I noticed that alternating angles are actually equal. Look at the difference in the reasoning. Okay, not very cheap, but it can be done. That is if you pick those 2. Can we just pick a different pair so we can prove it? I don't think you picked the best pair in the world. We did a lot of steps here to prove the parallel lines. There is always a faster way. Let's go back. Did you understand this way, however, the way you chose? I just needed to show you that you can do anything. Now let's go and just look closely at this. Let me erase a few things. We would like to prove that this line here is parallel to this line here. Do we have any 2 angles anywhere else that you may want to prove are equal? you can prove S3 and T2. So if I pick S3 and prove that it is equal to T2, I will be done. Here, I think that pair is a bit easier because I believe T2, before we forget, T2, remember our cyclic quad? Yeah. T2 is equal to what? D2. To D2. To D2. These are angles in same segment. So choosing is also a very important thing. You learn that with time, that you don't have to choose the worst ones. You learn how to choose the best ones as you go. But how many of you still remember that this thing was a tangent here? So if I want to talk about this S3, can you see what it should be equal to right now? It will be equal to D2. So S3 is also equal to D2. And this is tan chord theorem. Now, the two angles I was targeting, I'm already done. Oh. Now remember, we are saying if these two lines are parallel. There it is. Were you failing to see it, my dear? Okay, so at this point, we have just proved that which two angles are equal at this point? T2, therefore T2 is equal to S3. The moment T2 becomes equal to S3, then we were actually thinking these two lines are parallel. But now we are very sure they are parallel because we notice that angles that are supposed to be alternating are actually equal to each other. Am I making sense there? Okay, so let's write that statement. So because that one is the case, so from here you also just write that same statement. You say PT must be parallel to TW. What's the reason? It's still alternating. By the way, it's not just Z that you use. You can use F as well. You can use corresponding angles if you find them. For this one, however, it was a bit difficult to work with corresponding because of the way it looks like. Because, there was no F that's visible that you could use. All right, let's quickly go to the next sum quickly, and let's just talk about a few things if possible. I don't think they still feel the same way as the first day. Before I do anything at all, remember I wanted to talk about this whole tangent thing. So before you forget what I said, let's look closely at this diagram. Yeah, HC itself is a tangent here. So at least we know that we have a tangent for real, this one. I mean, it's already a given tangent, so there are no two ways about it. There is this angle between a tangent and a chord. We are just waiting to get good answers here. Right. That's a tangent. We have everything. We have parallel lines as well. Do you see them? Okay, as long as you are seeing the parallel lines, we can use them. However, what I'm interested in is to prove this one with you right now. I want us to find FC together. Do you have FC? You will see what I meant just a few minutes ago. Here is FC, there. Such a teeny weeny one, right? Prove that FC is a tangent to GCB. Look at where GCB is, right here. I'm sure you want to say, no, it's not a tangent, sorry. But they want you to prove it's a tangent. They've already established it is a tangent. So what? Do you see the little triangle I mentioned before? You go to the first time the line is touching the triangle. Do you see where it's touching? At C. Now, there is an angle that the line will make with the shape. Where is that angle? C2. So you just require to prove that C2, if this was really the angle between a tangent and a chord, it will be equal to which angle, people? B1. So your job is to prove that C2 is equal to B1 by any means possible. If you can prove that C2 is equal to B1, you will be done. Let's do it. Remember our target. Remember our target, people. I think I already want to say C4 is equal to B1, but I don't know if that is going to help. Are we together? Oh, we are now calling our parents. Please come. She's trying to kill us. Is that one? Okay. Yes. Guys, is it... Let's find B1. The only angle which I can see that's equal to B1 at this point. I can see two angles at least. I'm seeing E. How many of you are seeing that E is equal to B1? Angle E. Angles in same segment. But I was actually distracted by C4 being equal to B1 here. Right? Okay, which one will work? Now, which one will be friends with C? I think E will be better. Going via E will be better because E is actually in turn equal to C2. Can you see that? Look at E, look at C2, your parallel lines, guys. Yeah. You saw it. Yeah. So which method you take, you saw me, I'm sure you noticed that I didn't quickly notice that B1 was equal to E. I first of all said C4. But after some time, I then changed because I wanted C2, and I didn't have anything that was equating C2 and C4, or were we told that they were equal? We weren't. So therefore, that's why I chose the other way around. So that's the thinking process that after some time, you will be able to do it so easily. So for now, I just want to highlight this bow tie that we are using. Those two angles are subtended by the chord CD. So I can safely say B1. This is my first step. By the way, this thing shouldn't even be visible when you're doing it. You want to get there, but this is your strategy. But let's just go. B1 is equal to E. What was our reason for it? Angles in same segment. Okay. Right. But after that, I'm going to do this. I'm going to remove the angles in same segment since you can see them now. Let's see something else. I want you to now focus your attention on these parallel lines now. This is parallel to that one. And if I do so, and I put this line here, how many of you are seeing the Z that I wanted you to see? Which angle is equal to E then? But C2 is equal to angle E. What is our reason? Alternating angles. So alternating angles, which one are the parallel lines? AC parallel to ED. All right. Now, after you do that, what conclusion can I make here? Are you beginning to get half of what I'm saying? Or maybe everything that I'm saying? I'm content with that actually. Well done. So B1 is equal to C2 now. Now we can conclude from these two statements. But the moment I conclude that, then I am agreeing that that thing is a tangent. Because remember, we looked at, if we can just prove that this is equal to that, then it means this line here must be a tangent at that point. So it's a very good procedure to follow. Let me just write you have to say, therefore FC is a tangent. Therefore FC is a tangent to circle GCB. You can write everything, especially if you're afraid that you may lose your marks. Don't forget the reason. If you forget the reason, then you worked for nothing. What's the reason? No, you'll only lose 1 mark. Converse Tan-Chord theorem. That's why we are so sure. Converse Tan-Chord theorem. So I am going to let you prove that D1 is equal to G3 as well as number C. Do it as fast as you can because I believe you can do this. All right. All right. So let's do the last part of this. Guys, it's not always easy actually to get these things done, but you can always try, you know. If I say use one skill, there are 2 to 3 skills you can use here. Let me just say, if you use exterior angles of triangles, you know, say for starters, can you see how D1 is going to be equal to the sum of these two? Okay. I mean, just keeping it. Let me do that method later. Let me do this method first for starters. I want to just show you that D1 could have been something else. Which one is that? What can we say about D1? We don't have angles that are just equal to D1, you know, on its own. So therefore it becomes tricky to solve it. So you form equations. So I'm going to say D1 is equal to C2 plus C3 for starters. And why am I so sure? Do you remember these lines are parallel? That's alternating angles, because whatever that line is, I'm going to call it EH, is parallel to AC. This is not simple, but it can be done. All right. Now, after you do this, then you're wondering, you have to get G3 to be equal to this as well, or find something else. So look at let me show you how interesting these things can get. So I'm going to write an expression for G3 this side. Do you see where G3 is? Let me use exterior angles of a triangle on it. Look at that. Do you see that triangle there? G3 will be equal to B1 plus C1. Let's write it down. Don't you worry. B1, that is why I was saying I'm not sure if you will be able to pick this up. But here we are. Exterior angle of a triangle is equal to sum of opposite interior angles. So they have to meet at one place. We have an expression for D1, and now we have an expression for G3. You have to change one after the other until they both have the same expression. So that's what we are going to do now. You can come closer if you need. Okay, now let's remind each other something. I'll say one statement at a time. Let me remove things that we don't need. Say, for example, now, who remembers that this line and that line are equal to each other? This line here, this chord, is subtending angle C3 at the circumference. Can you see that? And this chord is subtending angle C1. So these two angles, what do we know about them? Yes. So I'm going to write, but C1, let me say, but, no, I have C1 and C, okay. But C1 is equal to C3. Why am I so sure? Equal chords subtend equal angles. This is the short reason. I hope you can see what I'm going to do to that C3. I'm going to change it to C1. Okay, I'm done. It's almost like that one. I just don't want that C2. That C2 where it is, I don't really like it, because it has to be B1 one way or the other. But just remember what we learned, we proved before. Do you remember we proved it was a tangent at one point? We proved that this line here was a tangent to this circle. We didn't just prove that. We even mentioned on our own that C2 was equal to B1. Do you still remember that this one was proven? Right? So after I do this, I can then use these two statements and rewrite my D1. I'm about to rewrite my D1. In place of C2, what do you think I'm going to put? B1. In place of C3, what do you think I'm going to put? C1. So it's a therefore. Now, how many of us can see that D1 is now equal to G3? Yes.
I got that far. I got sort of, but like the other way.
So you got this far, but it was the other way around. You see, the thing is, you will get there anyway. Most of this, After some time, yes, I do understand that those things happen, but you have to try and get to the point. By the way, it wasn't the only one. I think I showed you that D1 could have easily been E plus C3. And you were going to actually solve it until you make them equal to each other.
Yes.
So it's a skill, and it's a skill you are going to use. Because of time, I'm not going to use another method. I'm just, however, going to prove that HDC, that one is a cyclic quad. Can I just conclude? I didn't conclude. Therefore, D1 is equal to G3. We proved that. So you have to conclude. All right, I have someone making funny sounds. I understand. It's Euclidean geometry writers. They do that to people. Why D1 is equal to G3? Oh, that's what we wanted to prove. We can see they are equal now, isn't it? We can conclude. No. They are equal. It's a conclusion you are making because you have two angles that are equal to the same thing. Therefore, those two angles must be equal to each other. It's just a conclusion you're making. It's a deduction, if I may. Right? Let's just try to hang in there. Look at what we have now. I'm not going to use funny methods here. So let's find HD. I think you found HD, and then that's FC. F is FC here. So this must be the cyclic quad we want to prove. We have many ways, except we don't have a bow tie inside. Can you see that? We don't have a bow tie. So I'm just going to target one thing. Like, for example, I'm going to target D3 because it looks good where it is. So I'm going to try and prove that D3 is equal to what? C3 and 4. I'm going to do my best to get there. I'm not sure now. Will I manage? Will I manage? Okay. So what is it that we remember about this whole thing? What is D3 equal to? Or who remembers what C4 is equal to? B1. It is equal to B1. Did we prove C4 to be equal to something interesting other than B1? We proved it to be equal to? Did we work with C4 at any point? C4 is a tangent. It's also equal to E. No, it can't be equal to G1. G1 is not at a good place right there. Okay. Yeah, it is a tangent. Yes, it's given. Remember, it's given as a tangent. C4 is equal to B1. True. I'm not arguing that. That C4 is equal to B1. Of course not. We're just saying, will we get to where we want to get to eventually? Guys, do you see that D3 is equal to G3? How many of you are seeing that? Yeah. So, yeah. So if I can, look at these corresponding angles. Like there. Can you see that? So already we know one thing. Let's write it down. So D3 is equal to G3. Let's stop there for a second. Why is that true? These are corresponding angles. What are the parallel lines? ED and AC. Agreed. Now, the problem we have is to move from C3 and 4 to make it equal to something else. Maybe G3. Wait, what was G3? B1 plus C1. So we have everything that we need. Do you remember G3 is equal to these two? So we just have to prove that C3 and 4 is equal to all of that. Perfect. Let me just write it down. But G3 is equal to B1 plus C1. This one was? How did we get that one? I wanted to say proven, but let me just write again exterior angle of a triangle. We are almost leaving. Whoever it is, you may let them know that we are done now. Of a triangle is equal to sum of opposite interior angles. Let's stop right there. Now, is C3, is there anything equal to B1 that you may want to let me know? Now I'm moving to C3 and 4 now. C4, okay. So C4 is equal to B1. Why did we say so? We are left with just one thing. We want C1. Is C3 equal to C1, people? Because that's the only thing left now. Perfect. But C3 is equal to C1. Do you remember the reason? Equal chords, equal angles. Like this. So if this is the case, then you can see that this angle that we are talking about is actually equal to G3. You see? So therefore, C3 plus C4 is equal to B1 plus C1. So I want you to look at this statement and this statement. What can we say about the two now? Can you see they both have B1 plus C1 and C1 on the other? Okay. Are you underage for this? And so G3 must be equal to C3 plus C4. But our journey wasn't for us to prove that G3 is equal to C3 and C4. It was to prove that D3 is equal to that. So how many of you are still remember the, wait. We have to see something. We wanted to prove that D3 is equal to all that. So can I finish and say which is equal to D2? This thing, G3, is already equal to D3. So can we conclude this one here? Are you seeing it? So it means these two here must be equal to each other. Are we together? Okay. Now, as a result of all of that, you remember what's the name of the cyclic quad? HDFC is a cyclic quad. And who remembers the reason? Converse exterior angle of a cyclic quad. Okay, so we will keep this one with us. Whenever you need it, whenever you want to do the revision on this lesson, you let me know. So that's what, or you can say exterior angle is equal to opposite interior angle. Guys, that's what we had time for.